Hello everyone, I'm Emre, and today I'll talk about our just-in-time framework for tracing distributed applications. So debugging distributed systems is very challenging because of the difficulty of knowing where the problem is coming from. It could be in one of the many components that comprise the system. It could be in one of the several stack levels that the components are hosted on, like the virtual machine or the hypervisor or the kernel. And it could also just be like an emergent behavior that arises from these intercomponent relations that only happens when you put everything together and run it and scale. So today's debugging methods rely on instrumentation points to find out where the problem is coming from, like John has talked about. The problem with this is that different problems benefit from different instrumentation points. And if you want to instrument everything to catch any possible problem that may happen in the future, then you will be just collecting instrumentation data with your system instead of doing useful work. So today, what developers do is they start with a bare minimal amount of instrumentation in the running system, and then when a problem happens, they try to kind of guess where the problem is coming from. And if you can't find the problem, then you inject more instrumentation, you run it again, and then you kind of try to narrow down the source of the problem just over and over again with this manual iterative approach. So our research question is whether we can create a continuously running instrumentation framework for production distributed systems that will automatically explore these instrumentation choices across the different stack levels for a newly observed performance problem. The key insight that we use to realize this system is that performance variation indicates where we need more instrumentation. So on this graph, you see a request. That's basically the nodes of this graph represent events happening across systems, and the edges represent happens before relationships, and then the time flows like to the right, and the hierarchy of the system is to the bottom. And this is a read request from storage. So it starts at the client, then goes through the load balancer, and then does some operations at the backend services, and then returns to the client. Now, if you have a lot of read requests in a system, and they are expected to perform similarly, then they are expected to perform similarly. And if we trace a bunch of these read requests and we compare their traces, if one of them, for example, takes a lot longer than the other ones, then this performance variation would be a good indicator of where we need more instrumentation. So here you can see the read component is taking a variable amount of time between requests, and we can actually add more instrumentation to the read component automatically without relying on the manual analysis of developers. The key enabler that lets us get these graphs from distributed systems is WorkflowCentric Tracing, and it works by propagating a request ID with the request and recording events accordingly. The granularity of the data that's available to us is determined by the instrumentation that's already in the system. So the vision of Pythia is, I'll just go over it now, but basically it's a system that first gathers these workflow skeletons in the form of graphs and extracts critical paths from them and groups them based on performance expectation. Then we identify which of these groups have high performance variation, and we localize the performance variation within the group. After that, we can enable and disable additional instrumentation and start the cycle again to collect new data and enable more instrumentation. Instead of performance variation, we could also look at consistently slow groups as a second signature of performance problems. So today I'll talk about the more challenging aspects of this framework, which are the grouping, the localization of problems, and also deciding what to enable next. So the grouping basically is grouping workflows that are expected to perform similarly. And this expectation depends on the application that's being debugged. But a generally applicable expectation that we found is that the requests that are of the same type that access the same distributed system components generally should perform similarly. But additional application-specific details could be also incorporated. For example, if you're a storage system, maybe you could say read requests that are also of similar size should perform similarly. Yeah, so for example, here's a group of read requests and a group of, for example, authentication requests. And the second challenge of this framework is the localization. So the localization is in two stages. First of them is among the groups that we have collected, and the other ones within the groups. And to localize something, we need to order these groups based on a metric, which is basically how we quantify performance variation. There are multiple metrics that we can use to measure variation, like variance or standard deviation is one thing. Another one is coefficient of variance, which is the standard deviation divided by the mean. It's intuitive because if something has a smaller mean compared to the standard deviation, it would make more sense to prioritize exploring that. But in practice, actually, if you have a very small mean of some edges, then this could result in a very high coefficient of variance. And we don't really want to explore some things that take microseconds. So it's a trade-off. And we could also look at multimodality as a signal of problems. So if we have a distribution that has multiple modes, we could maybe enable something that would explain why some of them take longer than the other ones. And the third challenge is deciding what to enable after we have localized the problem. For this, Pythia uses a search space and search strategies. The search space is basically how we represent all of the instrumentation that Pythia can control. And the search strategies are ways to traverse this search space. So the search space helps us find the relevant next trace point after the problem is narrowed down. We want the search space to be quick to access and compact, while also limiting our search to a relevant set of trace points. And the search strategies, we also want them to quickly converge on problems and also keep the instrumentation overhead low by not enabling a lot of things. So there are many possible options for the search strategies. So in our full design, we have a pluggable search strategy, which for maybe each distributed application, you could devise your own search strategy. So after you enable more instrumentation, like I said, you come to the beginning and you collect more instrumentation data to keep going with the cycle. So I'll go over just a little bit of experiments. Here's one example where we validate our approach using OpenStack. OpenStack is basically an open source platform for clouds. It's used in MOC. And here's a bunch of requests to OpenStack and their corresponding latencies. So in the top, you see the server create request group actually has a very high variance and also very high mean latency. And compared to all of the other requests like floating IP allocation or listing the servers, this one definitely seems to be the problematic group. So Pythia would, in the localization step, in the grouping step, out of all of the requests, Pythia would group the requests into these rows that you see here. And in the localization step, it would focus on the server create group. And we actually run Pythia online on our own OpenStack, where Pythia then localizes the variation into a semaphore in the server create request. And after enabling the instrumentation in that semaphore, which reports the number of requests that are waiting on the semaphore, we see that the request latency is grouped into 3 different groups, where the fastest one has nobody waiting on the semaphore, second fastest one has like 1 to 3, and the other one has 4 and more. So the takeaway from this is that Pythia's approach can actually identify the instrumentation that's needed to debug this problem, and we have also, so that's the takeaway. And it's, in conclusion, it's very difficult to debug distributed systems, and automating instrumentation choice is a promising solution to overcome this difficulty and help debug distributed systems. Thank you.